you ever wondered why your phone or laptop battery doesn't last as long as it used to? Today, we're diving into the science behind battery aging and why batteries lose capacity over time. Understanding this process can help you make smarter choices about your devices and their maintenance. Let's start by exploring what happens inside a battery as it gets older and why this gradual decline is inevitable for all rechargeable batteries. Battery capacity refers to the amount of energy a battery can store and deliver to power your devices. When new, batteries provide maximum capacity, but over time this gradually decreases. This reduction means your phone, laptop, or electric car won't run as long on a single charge. Capacity is measured in milliamp hours or watt hours depending on the battery type. Let's see why this number changes as batteries age. Inside every battery, chemical reactions occur to store and release energy. Most modern batteries like lithium-ion rely on the movement of ions between electrodes. Over time, these reactions become less efficient, leading to reduced capacity. The materials inside the battery degrade and the structure changes, making it harder for the battery to hold a charge. This chemical aging is a key reason batteries lose capacity. Every time you charge and discharge a battery, it completes a cycle. Batteries are rated for a certain number of cycles, typically hundreds or thousands. Each cycle causes tiny changes inside the battery, slowly reducing its capacity. The more cycles a battery goes through, the more its performance drops. This is why older devices often need to be charged more frequently. Electrodes inside a battery are crucial for storing and releasing energy. Over time, these electrodes degrade due to repeated chemical reactions. Tiny cracks and changes in structure make it harder for ions to move efficiently. This degradation is a major factor in capacity loss, as the battery can no longer store as much energy as it once did. Lithium-ion batteries, a layer called the solid electrolyte interface (SEI), forms on the electrode surface. This layer is essential for battery function but grows thicker with each cycle. As the SEI thickens, it consumes active material and increases resistance, reducing the battery's capacity and efficiency. Managing SEI growth is a challenge for battery designers. Temperature plays a big role in battery aging. High temperatures accelerate chemical reactions and can cause faster degradation of battery materials. Conversely, very low temperatures can reduce performance and cause irreversible damage. Keeping batteries at moderate temperatures helps preserve their capacity and extends their lifespan. Frequently discharging a battery to very low levels can accelerate capacity loss. Deep discharges stress the battery's internal structure and can cause permanent damage. Most modern devices have safeguards to prevent deep discharge, but it's still best to avoid letting batteries run completely empty whenever possible. Overcharging a battery can also reduce its capacity. When a battery is charged beyond its recommended voltage, it can cause excessive heat and chemical changes, leading to faster degradation. Modern chargers usually prevent overcharging, but using the wrong charger or leaving devices plugged in for too long can still pose risks. As batteries age, their internal resistance increases. This means it takes more energy to deliver the same amount of power, reducing efficiency and capacity. Higher resistance also leads to more heat during charging and discharging, which can further accelerate aging. Monitoring internal resistance is important for battery health. Some older battery types like nickel-cadmium suffer from the memory effect. If they're repeatedly charged before being fully discharged, they remember a lower capacity and deliver less energy. While modern lithium-ion batteries don't have this issue, understanding memory effect helps explain why some batteries lose capacity faster than others. Over time, the materials inside a battery physically change. Electrodes can swell, shrink, or crack, and separators may degrade. These physical changes disrupt the flow of ions and reduce the battery's ability to store energy. Manufacturers are constantly working to improve material stability to slow down this process. Fast charging is convenient, but it can accelerate battery aging. Rapid charging increases heat and stresses battery materials, leading to faster capacity loss. While most devices are designed to handle fast charging safely, using slower charging methods can help preserve battery health over time. Modern devices use battery management systems (BMS) to monitor and control charging, discharging, and temperature. BMS helps prevent overcharging, deep discharge, and overheating, all of which can reduce capacity. Good battery management extends battery life and keeps your devices running longer. Environmental conditions like humidity, dust, and vibration can affect battery health. Exposure to moisture can cause corrosion, while dust and vibration may damage internal components. Keeping devices in clean, dry environments helps preserve battery capacity and prevents premature aging. Even when not in use, batteries slowly lose charge through self-discharge. This process is faster in older batteries and can lead to capacity loss over time. Self-discharge is influenced by battery chemistry and storage conditions. Storing batteries at moderate temperatures and keeping them partially charged can reduce self-discharge. Calendar aging refers to capacity loss that happens simply due to the passage of time, regardless of usage. Chemical reactions inside the battery continue even when it's not being used, slowly degrading materials. This is why batteries lose capacity even if they're rarely charged or discharged. Quality of battery manufacturing affects how quickly capacity is lost. High-quality materials and precise manufacturing processes result in longer-lasting batteries. Cheaper batteries may degrade faster due to impurities or poor construction. Investing in reputable brands can help ensure better battery performance. Different battery types age in different ways. Lithium-ion batteries are more resistant to memory effect but still suffer from capacity loss. Nickel-based batteries degrade faster, while lead-acid batteries have their own aging mechanisms. Understanding your battery type helps you manage its lifespan more effectively. How you use your devices impacts battery aging. Frequent charging, deep discharges, and exposure to extreme temperatures all accelerate capacity loss. Using devices gently and following manufacturer guidelines can help preserve battery health and extend its usable life. Proper storage can slow down battery aging. Store batteries in cool, dry places and avoid full charges or deep discharges before storage. Keeping batteries at around 50% charge is ideal for long-term storage. These simple tips help maintain capacity and prevent unnecessary degradation. As batteries age, you'll notice signs like shorter run times, slower charging, and increased heat during use. Devices may shut down unexpectedly or require more frequent charging. Recognizing these signs can help you decide when it's time to replace your battery or device. When a battery loses too much capacity, replacement is often the best option. Many devices allow for battery swaps while others require professional service. Choosing a high-quality replacement can restore performance and extend device life. Always follow manufacturer recommendations for battery replacement. Old batteries should be recycled properly to prevent environmental harm. Specialized recycling centers safely handle battery materials and recover valuable components. Never throw batteries in the trash as they can leak chemicals and cause pollution. Recycling helps conserve resources and protect the environment. Researchers are constantly working to improve battery technology. New materials, better designs, and smarter management systems aim to slow capacity loss and extend battery life. Innovations like solid-state batteries promise even greater longevity and safety. The future of batteries looks bright with longer-lasting devices on the horizon. Adopting smart charging habits can help preserve battery capacity. Avoid charging to 100% all the time, unplug devices when fully charged, and use original chargers. These practices reduce stress on battery materials and slow down aging, keeping your devices running longer. Many devices now include battery health monitoring features. These tools track capacity, cycle count, and charging habits, helping users manage battery life. Regularly checking battery health can alert you to issues early and guide you in making better usage decisions. There are many myths about battery aging, such as needing to fully discharge batteries or avoiding overnight charging. Modern batteries are designed to handle typical usage patterns, and following manufacturer guidelines is more important than outdated advice. Understanding the facts helps you care for your devices properly. Future holds exciting possibilities for battery technology. Researchers are exploring new chemistries, improved materials, and advanced management systems. These innovations aim to reduce capacity loss, increase safety, and make batteries more sustainable. Stay tuned for breakthroughs that will change how we use and care for our devices. Summary: batteries lose capacity over time due to chemical, physical, and environmental factors. Understanding these processes helps you make informed decisions about device usage and care. By adopting smart charging habits, monitoring battery health, and recycling old batteries, you can extend battery life and reduce environmental impact. The journey of battery technology continues, promising longer-lasting and more reliable devices for the future.